Welcome back to Ajua Biotech, your channel for all things science. Today we're diving into a crucial concept in analytical chemistry, internal standards. If you want to boost your analytical accuracy, stay tuned. Internal standards are vital in quantitative analysis. They help correct for variations in sample preparation, instrument fluctuations, and other procedural inconsistencies. Imagine you're measuring the concentration of a substance in various samples. By adding a known quantity of an internal standard to each sample, you create a reference point. The internal standard should be chemically similar to the analyte, but not present in the samples naturally. It compensates for any losses and ensures more reliable results. Step 1. Choose an appropriate internal standard. Step 2. Add it in a consistent amount to all your samples, standards, and blanks. Step 3. Measure the response ratios. Step 4. Calculate the analyte concentrations using the internal standard as a reference. The benefits? You get increased accuracy, reproducibility, and confidence in your results. Internal standards are especially useful in chromatography, mass spectrometry, and other analytical techniques like Western blot. So if all that did not make much sense, didn't give you a good grasp, here's another way to look at it. Internal standards can also be used and can be crucial in the construction and interpretation of standard curves for dose response experiments, particularly in fields like pharmacology, toxicology, and biochemistry. Here's how they're used in those instances. Internal standards are compounds added in a constant amount to all samples, standards, and blanks in an analytical experiment. They serve multiple purposes. Firstly, normalization. These compensate for variability in sample preparation, instrument response, and experimental conditions. Secondly, accuracy and precision. They improve the accuracy and precision of quantitative measurements by correcting for losses during sample preparation and analysis. The steps involved when using internal standards for dose response curves look something like this. The first is the selection of internal standards. So choose an internal standard that is chemically similar to the analyte of interest but does not interfere with its detection. It should have similar chemical and physical properties to the analyte to mimic their behavior during analysis. The second is the preparation of standard solutions. You prepare a series of standard solutions with no concentration of the analyte. You add a constant amount of the internal standard to each of these solutions. The third step is your sample preparation. So you've done your standard solutions, now you're doing the samples. And here you prepare the samples under investigation, adding the same amount of internal standard to each sample as was added to the standards. And then you go on to your analytical measurement where you analyze both the standard solutions and the samples using an appropriate analytical method such as HPLC, GCMS, or LCMS. You measure the response, for example, the peak area or height for both the analyte and the internal standard in each solution. Then you want to calculate the response ratios. So here you calculate the ratio of the analyte response to the internal standard response for each standard solution as well as the sample. This ratio helps in minimizing variations due to experimental inconsistencies. You typically would want to construct the standard curve, so you plot the response ratios So this is the analyte versus the internal standard of the standard solutions against the known concentrations of the analyte. You would fit a regression line or curve to these points in order to generate the standard curve. The standard curve is then used to determine the concentration of the unknowns. So you use the standard curve to determine the concentration of the analyte in the unknown samples by comparing their response ratios to the standard curve. Let's have a look at some examples. So in pharmacokinetics, when studying drug metabolism, an internal standard structurally similar to the drug can be added to all calibration standards, so that's the standard curve components, and plasma samples. This corrects for variations in extraction efficiency and instrument response. The second example is in environmental analysis. For example, in pesticide residue analysis in food, an internal standard can account for matrix effects and recovery rate during sample preparation and analysis. So if you're following, internal standards are used in various types of experiments to improve the accuracy and precision of quantitative measurements. So they tend to serve as a reference to account for variability in sample preparation, instrument performance, and other experimental conditions. They are used in experimental settings like in chromatography, whether it's gas chromatography or liquid chromatography. And their purpose, once again, is to correct for variations in injection volume, sample preparation, and detector response. Examples include quantifying small molecules, metabolites, or drugs in complex mixtures. So a practical use would be adding a known quantity of an internal standard to each sample and calibrator in a GCMS analysis to quantify the concentration of an analyte that you're trying to work out. They may also be used in mass spectrometry. So here in gas chromatography mass spectrometry, liquid chromatography mass spectrometry, or in MALDI-TOF mass spectrometry, so matrix-assisted laser desorption ionization, time of flight mass spectrometry, long name. Once again, the purpose is to account for matrix effects, ion suppression, and variations in instrument sensitivity, and so it's used in proteomics, metabolomics, and pharmaceutical analysis. Another setting is in NMR spectroscopy to ensure accurate quantification of compounds in a mixture by comparing the integrals of the sample signals to the internal standard. It's used in structural elucidation and quantitative analysis of small molecules. An example is adding a known amount of tetramethylsilane, TMS, as an internal standard in HNMR spectroscopy for chemical shift referencing and quantification. In quantitative PCR, you may use an internal standard, and the purpose is to normalize the amount of starting material and correct for variations in PCR efficiency. It's also used in gene expression studies and viral load quantification. For example, using a reference gene as an internal control to normalize the expression levels of target genes in a qPCR experiment. Further on this example, so if you were doing experiments, for instance, where you're looking at the viral load, the proviral load in a HTLV1 experiment, you will have on the plate your series of diluted standards that represent different loads of the virus, different genomic loads of it. And then you will also have a well that you dedicate to a known readout, a known viral load of the virus, the HTLV1 virus. So having a known positive sample, known negative sample, that's just your positive and negative control. And then you have your samples from which you've extracted genomic DNA, and you don't know what the viral load is. But the internal standard in qPCR is more when the actual sample, you have a reference point within the actual sample. And in the case of qPCR, again, for the HTLV1, you will have a gene that you've targeted. And in our case, we were targeting the albumin gene. So the albumin gene, which is standard in all the cells that you're analyzing, in this case, is peripheral blood mononuclear cells. In all of them, you will have the albumin gene expressed. And so that's your internal standards with which you compare how many transcripts of the HTLV1 is incorporated. And you use that to work out your viral load, your proviral load. Okay, thanks for watching. If you found this video helpful, give it a thumbs up and subscribe to Adjoa Biotech for more science insight. Have questions or topics you want us to cover? Drop them in the comments below. Until next time, keep exploring the wonders of science.